When we look up at the night sky, immersed in the silent immensity, our language and our intuition can play a trick on us. We are used to a world with a ground beneath our feet and a sky above our heads. We think of up as the direction we point to, and down as the direction things fall. But what do up and down really mean in the dizzying vacuum of space? This seemingly simple question is actually an invitation to an extraordinary journey, one that will turn our perception of home upside down, taking us far, far beyond the planets we know. Because our home is not, as classic illustrations suggest, a flat disk of worlds spinning around a star. It is a colossal, complex, and mysterious sphere that surrounds us on all sides, an invisible architecture whose scale defies imagination itself. Imagine you are floating in the infinite blackness of space, far from Earth's familiar gravity. Where would you point to say up? To the North Star? To the center of the Milky Way? The unsettling truth is that, in the cosmos, up and down are purely relative concepts, dependent only on your point of view. But if, instead, we rephrase the question to what surrounds us in all directions, the answer turns into one of the greatest and most epic stories of modern astronomy. It leads us to a structure so immense, so vast, that sunlight traveling at almost 300,000 kilometers per second takes more than a year to reach its nearest boundary. We are talking about a sphere of ice, dust, and rock that defines the true frontier of our system. Today, we are going to travel there, and far beyond. We will cross known limits, dive into the deep and cold darkness, and use the eyes of our probes, telescopes, and simulations to answer what, in fact, exists above, below, and on all sides of our solar system, to the ends of the universe itself. To begin our journey, we need a map, and our first map, the one we all know from school books, is a bit misleading. The classic image of the solar system, with the sun in the center and the 8 planets orbiting in concentric rings, more or less on the same level, describes what astronomers call the plane of the ecliptic. This plane is not a coincidence. It is a direct and fundamental heritage of our violent formation. About 4.6 billion years ago, our solar system did not exist. In its place, there was a giant, amorphous cloud of interstellar gas and dust, a cold and dark stellar nursery. Under the relentless force of its own gravity, this cloud began to collapse in on itself. As it contracted, a principle of physics called conservation of angular momentum kicked in. Think of a figure skater on ice. When she pulls her arms in, she spins faster and faster. The same happened with our primordial cloud. The contraction accelerated its rotation, and that rotation caused the cloud to flatten out, transforming the sphere of gas into a dense, swirling disk, the protoplanetary disk. In the superheated and dense center, pressure became so intense that hydrogen atoms began to fuse, and our sun was born. The remaining matter in this spinning disk gave rise to everything else: the planets, the moons, the asteroids. This is why the 8 planets, from Mercury to Neptune, a handful of dwarf planets like Ceres, and even the asteroid belt between Mars and Jupiter, all reside on this relatively thin and busy plane. It is our cosmic street, our reference. But the universe doesn't play by our rules. The formation of the solar system was a chaotic process. Complex gravitational interactions, especially with the gas giants Jupiter and Saturn, acted like cosmic slingshots. Billions of smaller objects, icy and rocky planetesimals, were thrown far away on random trajectories. Some were ejected forever, becoming lonely travelers in interstellar space. Others, however, were thrown into immense, highly inclined orbits, which took them far above and far below our cosmic floor, the plane of the ecliptic. It is exactly here that our idea of a flat solar system begins to unravel. Above and below this busy disk, where life flourished, there is not an absolute void. There is instead the beginning of a vast and sparse sphere, a domain of lonely and icy objects that are the first echoes of the true and surprising limit of our home. Our journey out of the plane truly begins where sunlight is already weak and diffuse, far beyond the orbit of Neptune, about 30 astronomical units, AU, from the Sun, remembering that 1 AU is the distance from Earth to the Sun, about 150 million kilometers. Welcome to the Kuiper Belt. Theoretically proposed by astronomers like Kenneth Edgeworth and Gerard Kuiper in the 1940s and 1950s, but only confirmed in 1992, this belt is like a larger, darker, and much colder version of the asteroid belt. It stretches from approximately 30 to 55 astronomical units from the Sun and is a colossal ring of icy debris, leftovers from the system's formation. It is estimated to contain hundreds of thousands of bodies over 100 kilometers in diameter and perhaps trillions of comets. The objects here are composed mainly of volatile ices, like frozen methane, ammonia, and water, and we have already been there with a robotic representative. On January 19, 2006, NASA launched the New Horizons probe. After a 9.5-year journey through the solar system, it made history. On July 14, 2015, New Horizons flew by Pluto, revealing for the first time an incredibly complex and active world, with vast plains of frozen nitrogen, like Sputnik Planitia, and towering mountains of water ice. This historic visit not only gave us the first detailed look at Pluto, but also proved that it was not a loner. It was, in fact, the king of a new cosmic province, the Kuiper Belt. It is the largest known object in this region and shares its neighborhood with other fascinating dwarf worlds like Haumea, Makemake, and Quaoar. After its primary mission at Pluto, New Horizons continued its journey. On January 1, 2019, it flew by Arakoth, a primitive object 6.5 billion kilometers from Earth. Arakoth looks like two flattened snowmen delicately stuck together, a contact binary that gave us an extraordinary glimpse of what the building blocks of planets, the planetesimals, might have looked like in their most primordial state. Most objects in the Kuiper Belt orbit in the same general plane as the planets, forming a thick disk. However, something strange was noticed. The orbits of some of the most distant objects are inexplicably clustered, their farthest points from the Sun all pointing in the same direction, as if an invisible gravitational hand were hurting them. This orbital anomaly led to the Planet 9 hypothesis, a theoretical world, perhaps with 5 to 10 times the mass of Earth, in an immense and eccentric orbit that would take thousands of years to complete. This long-range gravitational force could explain the behavior of these distant bodies. The search for this ghost planet is one of the most exciting and controversial hunts in modern astronomy. If the Kuiper Belt is a relatively orderly cosmic suburb, the next region is the wild zone, the lawless frontier. Welcome to the scattered disk. As the name suggests, this region is anything but organized. It overlaps with the Kuiper Belt at its inner edge, but extends much farther into space and, crucially for our question, far above and below the plane of the ecliptic. The objects here are the true rebels of the solar system. The most accepted theory is that they originally formed in the Kuiper Belt, but were scattered by gravitational encounters with the ice giant Neptune, especially during the planet's primordial migration to its current orbit. A gravitational push sent them into these immense, highly eccentric, very elongated, and inclined orbits. The largest known dwarf planet in the solar system, Eris, lives here. Discovered in 2005 by astronomer Mike Brown's team, Eris has a mass slightly larger than Pluto's. Its orbit, however, is radically different. It takes about 557 years to go around the Sun, and its inclination is an impressive 44 degrees relative to the plane of the planets. Sometimes it dives close to Pluto's orbit, but at its farthest point, it travels to almost 100 astronomical units from the Sun. The discovery of Eris, a body as massive as Pluto, but clearly part of a much larger population of objects, was what forced astronomers to formally redefine what a planet is in 2006, leading to Pluto's reclassification as a dwarf planet. Another fascinating resident of this region, which defies our classifications, is Sedna. Discovered in 2003, Sedna has one of the most extraordinary orbits we know. It takes about 11,400 years to complete a single lap around the Sun. At its closest point, it gets to 76 astronomical units from the Sun, far beyond the Kuiper belt. But at its farthest point, it travels to almost 1,000 astronomical units. Its orbit is so detached from Neptune's influence that scientists wonder what put it there. A star that passed close to our solar system billions of years ago and pulled Sedna into this bizarre trajectory? Was it captured from another star system? Or is it one of the first inhabitants of an even more distant structure? Sedna is a clear sign that we are approaching an even more fundamental and invisible frontier. So far, our journey has been through regions defined by rock and ice objects. Now, we approach an invisible boundary, made not of solid matter, but of wind, plasma, and magnetism, the edge of the heliosphere. The heliosphere is a gigantic bubble created by our own sun. Our star is not a static sphere of fire. It constantly emits a stream of charged particles, electrons and protons, in all directions. This is the solar wind. Traveling at supersonic speeds of over 400 kilometers per second, this wind carries the sun's magnetic field with it, inflating a vast magnetic bubble in the interstellar medium. This bubble is, in essence, the sun's outer atmosphere and our first and most important line of defense, protecting us from about 70% of dangerous galactic cosmic rays, high-energy particles coming from supernovae and other violent events in the galaxy. But this protective bubble is not infinite. At some very distant point, the solar wind, weakened by distance, no longer has the strength to push back the interstellar medium, the gas and dust that exist between the stars. The boundary where the pressure of the solar wind balances with the pressure of interstellar space is called the heliopause. Crossing it means, in fact, leaving the sun's magnetic influence and entering interstellar space. And humanity, incredibly, has already done this. The Voyager 1 and Voyager 2 probes, launched in 1977 for a grand tour of the giant planets, are our most distant sentinels. In August 2012, at a distance of 122 astronomical units, Voyager 1 crossed the heliopause. Its instruments detected a drastic and sudden drop in solar wind particles and a massive increase in the intensity of galactic cosmic rays, irrefutable proof that it had left home. Voyager 2 did the same in November 2018, 119 astronomical units away, confirming its sister's crossing at a different location, which helped us map the shape of this bubble. These two small probes, now operating on the energy of a refrigerator light bulb and communicating through signals weaker than a falling snowflake, continue to send us data from interstellar space. They are the first and only human objects to breathe the air of other stars. But although they have left the sun's protective bubble, they have not yet left its gravitational reach. The true final frontier, the structure that truly surrounds us, is much, much farther away. Our journey has taken us past the rocky planets and the gas giants. We traveled through the icy ring of the Kuiper belt and the chaotic zone of the scattered disk. We crossed the magnetic boundary of our system, the heliopause. And yet, we haven't truly left the solar system. It is here, in almost absolute darkness, where sunlight is weaker than that of a single candle seen from kilometers away, that we find the most vast, ancient, and mysterious structure of all, the Oort Cloud. This is what answers our initial question. What exists above and below the solar system? The Oort Cloud. It is not a disk, nor a ring. It is a colossal spherical shell, a swarm of trillions of icy bodies that surrounds the entire system, extending in all directions and defining the gravitational boundary of the sun's domain. Its existence was first proposed in 1950 by Dutch astronomer Jan Oort. He was studying long-period comets, those that take thousands or millions of years to orbit the sun, and noticed a curious pattern. They didn't come from the plane of the ecliptic, like short-period comets. They came from all directions of the sky, completely randomly. This strongly suggested that their origin was not a disk, but a spherical reservoir. These objects are believed to be the most primitive remnants of the solar system's formation, planetesimals that formed near the sun, but were thrown far away by the gravity of giant planets, like Jupiter, billions of years ago. Over time, the subtle gravity of neighboring stars and the Milky Way itself circularized their orbits, spreading them into this vast shell. The scale of the Oort Cloud defies imagination. Its inner edge, sometimes called the Hills Cloud, starts perhaps between 2,000 and 5,000 astronomical units from the sun. Its outer edge, however, can extend up to 50,000 or 100,000 astronomical units, which is more than halfway to the nearest star, Proxima Centauri. If the sun were a basketball in the center of a city, Earth would be a grain of sand 30 meters away, and the Oort Cloud would be a shell of dust and snowflakes enveloping the entire metropolitan area. The Oort Cloud has never been, and perhaps never will be, observed directly. Its objects are small, darker than coal, and incredibly distant. Its existence is a robust theory, inferred from the orbits of the icy messengers that occasionally visit us. But it is one of the most accepted in astronomy. It is the cosmic attic of our solar system, an icy and almost untouched archive of our origin. For the Voyager probes, the journey through the Oort Cloud has barely begun. It is estimated that Voyager 1, even traveling at 17 kilometers per second, will take about 300 years just to reach the inner edge of the cloud, and perhaps 30,000 years to cross it completely. When they finally exit the other side, their nuclear power sources will have run out millennia ago, and they will travel in silence. Only then will they have, finally and without a shadow of a doubt, left the solar system behind. If this trip through the frontiers of our home is expanding your mind, consider subscribing to the channel. Your curiosity fuels our exploration, and we still have a lot of territory to cover, traveling to regions where not even our probes have reached. Crossing the Oort Cloud is like taking the last step out of the backyard. Now we are truly on the street, in interstellar space, the material that fills the vast abyss between the stars. And just like in any neighborhood, our location is not random. The sun and its planets are currently traversing a specific region known as the local interstellar cloud. This cloud is not like clouds on Earth. It is a region of gas and dust about 30 light-years across, slightly denser than the surrounding medium, but still an extraordinarily thin vacuum by our standards. We are immersed in it, but this cloud, in turn, is inside a much larger structure, the local bubble. Imagine a gigantic cavity in the interstellar medium, carved out over millions of years. That is the local bubble, a region about 1,000 light-years across, filled with rarefied and extremely hot gas, with temperatures reaching 1,000,000 degrees. The origin of this bubble? The fury of dead stars. It is believed that about 14 to 20 million years ago, a series of supernovae, the cataclysmic explosions of massive stars, happened in this region of the galaxy. These explosions acted like cosmic bombs, pushing gas and dust outward and creating this vast low-density cavity. The Sun, on its orbital journey, entered this bubble about 5 to 10 million years ago by pure chance. Inside this hot bubble, there are wisps and denser, colder clouds, like the local interstellar cloud we find ourselves in now. Our current trip through it is temporary. It is estimated that in less than 70,000 years, the solar system will exit the local cloud and enter a neighboring cloud. Being inside the local bubble offers us a surprisingly clear view of the stars, as there is less dust to obscure the light. Above, below, and around us, in our stellar neighborhood, we are floating within the ghostly echoes of ancient supernovae. If the local bubble is our neighborhood, then the next layer is our city, the Milky Way. Our galaxy is a gigantic city of stars, a barred spiral galaxy with a diameter of over 100,000 light-years, containing between 100 and 400 billion stars. And, like any metropolis, it has its geography. The structure of the Milky Way is made up of 3 main parts. In the center, there is the galactic bulge, a dense and spheroidal region of older stars, which houses a supermassive black hole named Sagittarius A star in its heart. Surrounding everything, there is the galactic halo, a vast sphere of ancient stars, globular clusters, and, crucially, an immense amount of dark matter whose gravity holds the galaxy together. But the most iconic part is the galactic disk, where most young stars, gas, and dust reside. This disk is not uniform. It is organized into great curved avenues, the spiral arms. For a long time, it was thought that our solar system was located between 2 main arms, Sagittarius and Perseus. However, more recent observations, especially from the Gaia mission, revealed that we are, in fact, inside our own smaller structure, a spur or secondary arm called the Orion arm, or local arm. This arm is about 20,000 light-years long and houses not only the Sun, but also many of the brightest stars and constellations we see in the night sky, like those that form Orion, the Hunter. We are located about 26,000 light-years from the galactic center, roughly halfway to the edge of the disk. Our position, neither in the chaotic and irradiated center, nor on the desolate periphery, may be one of the factors that allowed life to flourish here. Above and below the plane of our galaxy, the spherical halo extends, a reminder that even our vast stellar city has a 3-dimensional architecture, with sparse and ancient suburbs far above and below the bustling spiral streets. Having explored our city, the Milky Way, it's time to step outside and see the neighborhood. No galaxy is an island. They cluster in groups bound by gravity, and ours is called the local group. This is our little condo of galaxies, a volume of space about 10 million light-years in diameter. The local group is dominated by 2 giants, our Milky Way and its larger neighbor, the Andromeda Galaxy, M31. Together, they contain about 90% of the mass and luminosity of the entire group. Andromeda, located about 2.5 million light-years away, is the farthest object we can see with the naked eye, a faint and diffuse smudge in the night sky. Besides the 2 giants, the local group is made up of more than 50 other galaxies, most of which are dwarf galaxies. Think of them as small villages or cottages orbiting the 2 metropolises. Among the most famous are the Triangulum Galaxy, M33, the 3rd largest in the group, and the iconic Large and Small Magellanic Clouds, irregular dwarf galaxies that are satellites of the Milky Way, visible mainly from the southern hemisphere. These dwarf galaxies orbit the larger ones, and many are slowly being cannibalized. their stars and gas being ripped away and absorbed by the Milky Way and Andromeda in a process of galactic merger that will last billions of years. The center of gravity of the local group is somewhere in space between the Milky Way and Andromeda, and these two giants are on a direct collision course. They are approaching each other at a speed of over 400,000 kilometers per hour and, in about 4.5 billion years, will begin a monumental cosmic dance, merging to form a single gigantic elliptical galaxy, which some have already nicknamed Milky. What exists above and below the local group is no longer the halo of a single galaxy, but intergalactic space, dotted by these islands of stars, all connected by their mutual gravitational dance. Zooming out once more, we realize that our local group, with its dozens of galaxies, is just a small part of an even grander structure. It is part of a vast archipelago of galaxies known as the Virgo supercluster, or local supercluster. This colossal structure contains more than 100 groups and clusters of galaxies and spans over 100 million light years. At its beating heart, about 60 million light years from us, is the massive Virgo cluster, a dense urban center with more than 2,000 galaxies. The immense gravity of this cluster acts as a brake, slowing down the expansion of galaxies in its vicinity, including our own local group. For decades, we thought the Virgo supercluster was the largest structure we belonged to. But in 2014, a new way of mapping the universe changed everything. A team led by astronomer R. Brent Tully analyzed the movements of thousands of galaxies, not just their positions. They realized that the Virgo supercluster was actually just an outlying arm of an even vaster and incomprehensible entity, which they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is our true cosmic province. With a diameter of 520 million light years, it contains about 100,000 to 150,000 galaxies. The definition of Laniakea is not based on how close galaxies are, but where they are going. It is a gravitational watershed. All galaxies within Laniakea, including the Milky Way, are flowing toward a common point, a massive gravitational valley called the Great Attractor. This point, partially obscured by our own galaxy, is a concentration of mass so immense that it pulls everything in our vast region of the universe toward itself. Up and down, now, are directions relative to this cosmic flow, into or out of the boundaries of this celestial province, defined not by walls, but by movement. If Laniakea is our province, what is the geography of the planet? What we see upon zooming out for the final time is the large-scale structure of the universe, an architecture of divine proportions known as the cosmic web. At this scale, galaxies are not randomly distributed. They are organized into a vast and intricate network that permeates the entire cosmos. The cosmic web is made up of three main elements: filaments, voids, and nodes. Imagine long, thin bridges of dark matter and gas stretching for hundreds of millions of light years. These are the filaments. Galaxies and superclusters like Laniakea are born and live along these cosmic highways, like bright cities lined up along a coast. Recently, the James Webb Telescope managed to capture images of one of these filaments, 3 million light years long, connecting galaxies in the early universe, visually confirming the existence of these structures. Where filaments meet and intersect, nodes form, dense and massive regions that house the largest galaxy clusters in the universe. And between this network of filaments and nodes, there are the great cosmic voids, immense, spherical, and frighteningly empty regions, hundreds of millions of light years across, where very few galaxies exist. The universe, on its largest scale, looks like foam, with matter concentrated on the bubble walls, the filaments, and almost nothing inside them, the voids. It is believed that more than 50% of all matter in the universe resides in these filaments. This colossal structure was seeded by tiny quantum fluctuations in the first instance after the Big Bang, which were stretched by the expansion of the universe to astronomical proportions. Finally, we arrive at the last frontier, the limit not of space, but of time. What exists beyond the cosmic web? The answer is more cosmic web. We don't know if the universe is infinite, but we know there is a limit to what we can see. This is the observable universe. Since light travels at a finite speed, looking far away is the same as looking into the past. The light from the most distant galaxies we can detect has traveled for almost the entire age of the universe, 13.8 billion years, to reach us. However, during all that time, the fabric of space itself has been expanding. This means that these galaxies are, today, much farther away than they were when the light left. Taking this expansion into account, the diameter of our observable universe is estimated at a staggering 93 billion light years. This is our bubble of vision, a sphere centered on us, whose limit is the point from which light simply hasn't had enough time to reach us since the beginning of time. And if we look at that boundary in all directions, what do we see? We don't see galaxies, but rather a wall of light, a fossil glow that permeates the entire sky. It is the cosmic microwave background, CMB. This is the remnant light of the Big Bang itself, the echo of creation. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. The CMB is a photograph of that moment, the oldest image of the universe we can ever get. It reaches us from all directions, forming a spherical shell that completely surrounds us. About 1% of the static on an old television is actually the detection of this primordial light. The tiny temperature variations in this radiation are the seeds that, billions of years later, would become the filaments, the voids, the superclusters, the galaxies, the stars, and finally, us. Our journey took us from the familiar rings of Saturn to the ghostly, icy shell of the Oort Cloud. We started with a simple question about up and down, and discovered that our cosmic home is not a flat disk, but an immense sphere of influence stretching for light years. In the face of the cosmic web, physically, we are smaller than a single atom in a vast ocean. It would be easy to conclude that we are insignificant. But looking at this fossil light of creation wrapping around us, another truth emerges. For 13.8 billion years, the universe expanded in silence. It was vast, complex, and violent, but it was not known. Until us, the iron in our blood, the calcium in our bones, and the carbon in our brains were all forged in the hearts of the stars we just explored. We are not merely tourists in this structure. We are made of it. We are the universe waking up. We are the cosmos evolving a way to look in the mirror and marvel at its own grandeur. Our significance is not measured by our size in light years, but by our capacity to wonder. We are the eyes of the universe, and through us, the cosmos finally finds its meaning. So, when you look up tonight, remember, you aren't just looking at the universe. You are the universe, looking back at itself. What exists above and below the solar system is the same as what exists in all directions, a series of nested layers of increasing complexity, a structure that repeats at ever larger scales. From the sphere of the Oort Cloud to the sphere of the observable universe, we discovered that we are at the center of our own perspective, wrapped in a 13.8 billion year history. Looking at the night sky is realizing that there is no void, but the continuation of our cosmic home in all directions, a rich texture that extends as far as light and time allow us to see. It is the ultimate journey to understand the totality of our home. and, by extension, our significant and interconnected place within it.